Here's a string ramp problem that I'd like to go over. We see the drawing here. We have a 2 kilogram block resting on this 50-degree incline, and we have it tied to a string over a frictionless, massless pulley here to another 2 kilogram mass. And one of the questions could be, what would the block's acceleration be if there were no friction? So we'll do that problem first. And then a second part could be, well, what if there was friction? Then determine what the coefficient of static friction would be. Okay? So I'm going to get a couple of sheets of paper here to overlay on top of it. And we'll start the first part of the problem. The first thing we want to do is draw a force diagram for each one of these blocks. So the first 2 kilogram block, okay, so there's point object number 1. Okay, and I'm just going to draw the string tension force going off that way. Now, in the first part of the problem, there is no friction. Okay, so what else do we have? Well, we have the block's weight, and that would be, remember, weight is equal to mass times gravity, right? According to Newton's second law. So if the mass is 2 kilograms and the acceleration of gravity is approximately 10, 9.8, but I'll just round off to 10, we get approximately 20 newtons of weight. So that's what this weight vector is right here. Okay, we also have the normal force perpendicular to the ramp. Normal force. And see, those are the 3 forces acting. No friction in this particular case. I'll draw the components of the weight vector. Those are the 2 short legs of the right triangle, where the hypotenuse is the vector 20 Newton weight. Okay, this right here, what is that? Well, we need to find out what that angle is. We know this is a 50-degree angle. Can we say that this is also 50 degrees? Yes. Okay, and I'll just go up here and we can see that if I draw that weight vector like this and draw a line perpendicular like this, this angle here is 50 degrees, just like this angle here, because it's a 90-degree angle here. 50, 90, this would be 40. 40 and 50 gives us another right triangle right here. Okay, so anyway, if this is a 50-degree angle, then this is also a 50-degree angle. So that means then that this component would be 20 times the cosine of 50 degrees, which is about 12.9 newtons. And then this would be 20 sine 50 degrees, and that's equal to about 15.3. Okay, so we have our 2 components of our weight vector laid out right there. So that's helpful. What else now? Well, we want to find the block's acceleration. Now that's along the ramp, right? So I'll just put a little dotted line here to remind you of what the ramp incline is. Okay, this can be kind of considered like our x-axis, right? Now we also have the other point object, the other 2 kilogram mass here, don't we? So I can draw that point object up here. That'd be number 2. And it's nice to kind of, since this pulley is only changing the direction, we can kind of in our mind straighten that out and avoid having the pulley change the direction, so that the weight of this 2 kilogram block, instead of pointing downward at 20 newtons, it's pointing to the right at 20 newtons. So we basically just leveled the playing field. Open that up, avoid the pulley problem and the direction problem, and now the weight of this 2 kilogram block, we can imagine is pulling to the right in a positive direction. And the string tension acting on this 2 kilogram mass here is pulling to the left with an equal magnitude but opposite direction of this tension force. So here's point object number 2. This was point object number 1. Okay, good enough. Now we can go ahead and write an equation for this free body diagram, and write a second equation for this free body diagram. Now this one's not too bad, right? When we only care about in the direction of the ramp. We want the block's acceleration along the ramp. So what would this be? Well, if we make to the right positive and to the left negative, that'd be like a negative t right there. We'd have 20 minus t. Remember, the sum of the forces is equal to ma, right? So 20 minus t is equal to the mass m of 2 kilograms times a. So there is one equation that we can use. It has two unknowns, but that's okay because we're going to get another equation from this free body diagram. Okay, now this free body diagram, remember again, the sum of the forces equals ma. In this case, it's this mass here, 2 kilograms, and a is going to be the same as this a because they're attached by a string that doesn't stretch and is massless. Okay, what would be the net forces? The net force would be this tension force pulling to the right, so that'd be T, and then plus a negative or minus any force that's directed down the ramp, which in this case would be 15.3. Okay, so now we have this equation here, T minus 15.3 equals 2A. Now we have two equations and two unknowns, and so an easy way to address this, I mean, you could always use direct substitution, but we can take and add these two equations together. That's a real nice nifty way of solving this type of a problem. So 20 minus t equals 2a, and then t minus 15.3 equals 2a. We'll just add those two equations together. Now when we do that, we see that this is a 20 minus t, and this is a positive t minus 15.3, so the t's actually subtract out, and we end up with 20 minus 15.3 equals 2a plus 2a, or 4a. Now if we take that, what does that equal to? That's 4.7 equals 4a, and so if we divide both sides by 4, we get a is equal to about 1.18 meters per second squared. So that's how fast, and that answer is a positive result, so that indicates that that is going upslope. It's going upslope. Parallel to the ramp, upslope, sliding up and to the right. Okay, with an acceleration of 1.18 meters per second. So that's the block's acceleration if there were no friction. Okay, and now I'll get another sheet of paper and we'll do the second part of the problem. What if there was friction? Okay, well, if there was friction, then we would there could be a static equilibrium, where it could be at rest. Okay, so let's go ahead. We already have some of that information done, but I can just redraw the force diagrams real quick. So there's point object number 1. Here's our ramp incline. We have our weight vector there of, we've already figured out it's 20 newtons. We'll split it up into its two components at right angles to each other. We remember this was 12.9 newtons and this was 15.3 newtons. We also have a normal force that is actually important in this case. We know this angle is 50 degrees. Okay, good. So that's for point object number 1. For point object 2, number 2, we have the tension, oh, I forgot the tension force, sorry. So we have the tension force this way, right? I better move this over. And we also have friction. I forgot to mention that one. So we have a friction force. And I'm going to do that in a special color, because remember, now there's friction. So that might be like this long or whatever. So I'll just put a lowercase f there, and I'll use purple to make it nice and bold. Okay, now let's draw the other one. I kind of messed up here, so I'm going to put it underneath. We have point object number 2. We have the weight of the other mass, the hanging mass, pulling. Okay, and that would be with a 20 Newton force, right, because its weight is 20 newtons. And then we have the tension force pulling the other way. So that'd be a negative T since it's pointing to the left. This would be a positive T for that one. So we have two force diagrams. Okay. Now let's see what we can do. Instead of letting the sum of the forces equal MA, we're going to let the sum of the forces on this one equal 0, because we're assuming that it's going to be in static equilibrium here. So we want to find out the coefficient of friction that would be needed in order to make it determine the coefficient of friction. We're going to put it in static equilibrium. Okay, so let the sum of the forces for this free body diagram here, set that equal to 0. And what would we have? We have the right hand force, which is tension, minus, we have two things that are fighting against the tension. We have the friction force, and we have that 15.3 Newton component of the block number 1's weight vector. Those are going to add up to 0. Okay, but we have two unknowns there, so we'll have to get another equation to help us solve for that. Now this one here, we have 20 and a negative T. So remember, the sum of the forces have to be equal to 0 there. So that would be 20 minus T equals 0, or in other words, T equals 20 newtons. That's good. We can substitute that in right here. Substitute that in. And so if we do that, we get, substitute in for this, we get T is 20, so I'll put that in there, minus F, minus 15.3 equals 0. So therefore, if we solve for F, I'll just add F to both sides. We get F is equal to 20 minus 15.3. Okay. And 20 minus 15.3 is 4.7 newtons. Now it didn't ask what the frictional force was, but that will be very helpful. What it asked for was the coefficient of friction, and that's mu. So we have to think about the fun formula. Remember the fun formula, where static friction is less than or equal to the coefficient of static friction times the normal force. Okay. Well, what's the normal force? It's 12.9. 12.9. So there we have, I'll put that in for N. And we know that the friction, in order to keep it at static equilibrium, is 4.7 newtons. I'll put that there. And we'll just set this equal to get our minimum value, and we can solve for mu. So mu then would be equal to 4.7 over 12.9, and that gives us 0.36. And that's our coefficient of static friction. Thanks a lot, guys.